Welcome back to Physics Fundamentals. In this video, I want to talk about two of the forces that you have the most experience with, weight and friction. We've already talked a lot about weight, even though we haven't called it that up to this point. The idea of weight is the gravitational force. An object that is in free fall is accelerating under the acceleration of gravity. And Newton's law says that every acceleration is caused by a force, so there must be some force of gravity equal to mass times the gravitational acceleration. Some people like insisting that this thing is called the weight and writing it using the letter W. I don't do that, because I find that calling every force F with a subscript for what kind of force it is makes everything make a lot more sense to me. But if you don't like subscripts, you might find that to be useful. And immediately, once I start talking about weight as a force, we start to run into the immediate issue. If I have a crate sitting on the ground, this crate has a weight, right? There is some mass of this crate, and that mass is going to cause a gravitational force to be pointing downward, which would cause the crate to accelerate downward. Except we know that that's not what happens. When we put a crate on the floor, the crate stays on the floor in almost all cases, right? I guess there is always the possibility that the crate breaks through the floor and falls down, but that's not supposed to happen. That's a sign of problematics. And so the answer to that is introducing a new force. We're going to call it F sub n. This thing is called the normal force, and the normal force is, for a horizontal surface, always going to counteract gravity. The normal force is the force that causes you to not fall through the floor. It is the force that the floor is applying to your feet to prevent you from falling in. We call it the normal force in the sense of perpendicular, right? Perpendicular, orthogonal, and normal are three terms that mathematics has for stuff that's at right angles to each other. And depending on the shape of the stuff you care about, you use a different one. So when you're talking about an area, a two-dimensional object like a floor, acting in a line, a one-dimensional object, the vocabulary for perpendicular in any direction that you look at them is normal. If you have a floor that is tilted, the normal force is going to point at a weird angle. For right now, we're going to stick with nice horizontal surfaces like floors and tables. So the normal force points straight up, the gravitational force points straight down. It makes our lives a lot easier. All right. But if we have that the normal force and the gravitational force are equal and opposite, then we know that the net force is zero. The object neither floats up nor sinks down in, which is exactly what we expect to happen, so we're very happy about that. At this point, you might be starting to think that I am talking about new things just for the sake of talking about them, but there is a method to all of this. I'm going to go back to our simulation on PhET, so I apologize that the screen is suddenly going to become a lot brighter. And I want to remind you of this simulation that we've worked with before. When we have this crate sitting on the skateboard and we push the crate, it's going to come up to some speed and it will continue moving at that speed indefinitely. If we have more weight, it takes more force to cause it to stop moving, but you have to apply a force to cause it to stop moving. We know, practically speaking, that that's not what is going to happen. If we have an object, let's use the two crates, that's what we had before, and we try to push them, there is going to be a frictional force. That frictional force is going to slow the object down once it stops moving and eventually bring that to a stop. And one of the things we know about friction is if we add more weight and try to push things, the more weight that is there, the faster it's going to slow down. All right, so if we're pushing the girl holding two crates, she's going to come to a stop pretty quickly. If we're pushing the girl and she's not holding crates, getting her to the same amount of speed is going to be much faster, and she's going to slow down a lot slower. Mathematically, this is actually very interesting because, well, we can start to think about the mass, but then after a little bit of thought, you'll realize that's not really what matters. If you have any experience in trying to move furniture or anything else of that sort, you may know that if you try to lift something up, even if you don't quite get it all the way off of the ground, pulling up on it as you push or pull across the floor is going to make sliding it a lot easier. So looking at the force is really what matters. It turns out, go back to my dark screen where we can breathe a sigh of relief. It turns out that it is the normal force that is our key here. So the force of friction is going to be equal to some constant. We call that constant the Greek letter mu. And we multiply that times the normal force. This constant is called the coefficient of friction. And if I come back to my simulation, one of the things that I went a little bit too fast for you to see in that first example, as I increase the applied force, the frictional force is going to grow at the same rate. But what you'll notice here is eventually when this crate starts moving, if you pay close attention to the friction force arrow, even though the applied force is always growing, at some point that friction force is going to stop growing and it's going to shrink, not a lot, but it's going to shrink instantaneously. And it should happen right about here. There it goes. It jumps down. And again, that's probably something that you have experienced in your life. If you are pushing something, the effort that it takes to get it started is the hard part. Once you get it started, you can keep it moving. And there is a reason for that. If you think about at the microscopic scale, objects are not rigid. Or objects that are rigid are not smooth. They have rough edges, some rougher than others. But if you have two objects that have rough edges and you push them against each other, what's going to happen is that those rough edges are going to settle in and lock it in place so it can't really move. And once you get it moving, it's going to skip across the top and then be able to move a lot more freely. So we call those two things static friction, which resists motion, and kinetic friction, which hinders motion. All right, so static friction, when the object is not moving, is going to resist the idea of moving at all. Kinetic friction, once it is moving, is going to cause a drag, so that as it's moving, it tries to slow down, and it takes effort to get things to continue onward. Generally speaking, there are two types of problems that you can look at involving friction. Either you know the materials and you are able to look up in a table or a database the coefficient of friction between them, or you have no idea and your goal is to figure out what the coefficient of friction is in the first place. Right? But the coefficient of static friction between two wooden surfaces we can look up and find is generally 0.40. And the coefficient of static friction, the coefficient of kinetic friction, are unitless quantities. They're just numbers. Consider a wooden crate with mass 75 kilograms on a hardwood floor. How much force must be applied to start this crate sliding? All right, let's see, what do we have? We have a coefficient of friction given to us, that's generally mu, 0.40. We have a mass given to us, 75 kilograms, and we're talking about an applied force. I'll put FA, and I'll put a nice question mark next to that. All right, that's what we need to know from this scenario, so I can scroll and give myself a little bit more space to work, put in my nice dividing bars. This is the type of problem that I find drawing a picture tends to be very helpful. Your picture doesn't have to be detailed. In fact, the less detailed, the easier it tends to be to read the picture. So there's my crate. It looks a lot like a crate, I know. But that simplicity is what's going to make our lives easier. We're trying to push this crate, so there is some applied force. That pushing is going to be counteracted by the force of friction. The force of friction, we know, relies on a normal force, and the normal force relies on gravity. And that also makes sense, right? The crate is on the floor is holding the crate up, so there's a normal force. The crate is presumably on Earth, so there is gravity pulling it down. This kind of structure of just drawing things out is called a free body diagram. We use a dot to represent our object. We start drawing arrows to represent all the directions that forces are going in, and we hope that everything works out nicely. I also notice here that we have forces going in all sorts of different directions. It turns out that if you think about the horizontal and vertical directions separately, everything is going to work nicely. So I know some things here. I know that the force of gravity is mass times gravitational acceleration. Mass is given to us, gravitational acceleration is not. but we'll assume that we are on the surface of Earth, so gravitational acceleration is 9.8 meters per second squared. From there, I'm going to grab out my calculator. 75 times 9.80 comes out at, well, 735, but I've only got two significant figures, so I'll round that and call it 740. Next, I know that the normal force is the opposite of gravity. And while I didn't mark it down here, the way that I've drawn this figure, gravity is kind of pointing downward, which we usually take as the negative direction. So the normal force, which is the negative of gravity, is going to be the negative of negative 740 newtons, which is positive 740 newtons. And then one other equation that I know is that the force of friction is equal to mu times the normal force. Although my force of friction is pointing to the left, so I guess I should call that a negative value. I know that mu is given to us as 0.40. And I just calculated that Fn is 740 newtons. My calculator tells me when I multiply those together, I get 296. But again, just two significant digits here, so I guess that's going to be 300 newtons, with that zero being significant. And then finally, our applied force is trying to counteract the force of friction. So this is not a formula that I know, but this is where looking at the free body diagram becomes so important. The applied force and the force of friction are trying to oppose each other. If we want this thing to get moving, our applied force has to be ever so slightly larger than the force of friction and in the opposite direction. Ever so slightly larger means that equal to within the significant figures we have, and 300 newtons. Right, so in order to get this crate moving, we are going to need to apply 300 newtons of force. That was a lot of hoops that we jumped through to get there. There was a lot of work that went into that one, and a lot of logical reasoning of thinking about this force is related to that force is related to the other force that we had to go through. But if you stop and you walk through it step by step, piece by piece, I think it should all make sense. I've spent enough time on this though. I think I'm going to wrap up with that. As always, thank you for joining me, and I'll see you in the next video.